Hello, DEF CON. Thank you so much for being here. It's like the second to last talk. It's a great turnout. I'm very honored to be here. My name is Yisrael Mirsky. I'm a Zuckerman Faculty Scholar at Ben-Gurion University and head of the Offensive AI Research Lab there. And with me here today are my brilliant graduate students who will be coming up on stage also to present. They did all the hard work. There's Daniel Eisenstein and Roy Weiss in collaboration with Guy Amit, who couldn't make it. Okay, so today we're going to talk about a new side channel attack against AI assistants that enables adversaries to read encrypted response traffic, such as responses from ChatGPT. Okay, so I'm not going to go into what are AI assistants. You guys all know this very well. You have OpenAI's ChatGPT, you have Google's Gemini, you have Microsoft Copilot, and the list goes on and on. And these AI assistants are integrated throughout industry in all different kinds of use cases. But what's more interesting to me is the use cases of the personal level, right? A lot of users are using these AI assistants, such as ChatGPT, to get personal advice. So for example, you may ask it some medical questions like, why do I have a rash on my back, right? And ChatGPT will get back to you and say, oh, I'm sorry to hear you have a rash on your back. Let me give some tips how to take care of that. Or maybe you may ask ChatGPT for some relationship advice. What are the signs my wife is having an affair, right? And get some good tips on there. Or maybe you're getting into hacking and you're going to ask ChatGPT how to get into your neighbor's Wi-Fi, right? Lots of good use cases. Or my favorite, a lot of people are using ChatGPT to edit their documents. They'll take whole documents or emails, dump it into ChatGPT and say, hey, make it better, or finish this paragraph, or what have you. And these are all very good and legitimate use cases. They're actually very productive for our society to help us progress and automate things. But the problem is that what happens if these chats aren't actually private? What happens if somebody could read these chats beyond, for example, OpenAI? Right, so this would be a huge breach in privacy. So in truth, we know they're encrypted, right? So, OpenAI is encrypting all the traffic going between the client and the servers. But is that enough? Maybe a little foreshadowing. So let me go back to the beginning of this story here. So several months ago, late at night, I was using ChatGPT for very important stuff, such as trying to figure out, what would the world be like if the every country had ninjas, but Japan had the worst ninjas, right? So as I'm looking at the text glide across the screen and looking at this very insightful and thoughtful response, it kind of hits me. Wait a second. Could it possibly be that OpenAI is sending every single word as a separate packet? And could it be that every single packet has no padding, so I can count the number of characters in each of these words? So I open up Wireshark, and sure enough, what do I see? For every single word that's being sent from the AI assistant, I see another packet, and the size of that packet increases. And if I take the delta between these packets, I know exactly how many characters in every single word. And I could use this, for example, to try and guess what those words are and potentially learn or identify what is being said in those responses. Now, before I go on to explain how we figured out what those words are, I need to take a little bit of a technical aside and clarify something. That what ChatGPT and all these different AI services are sending are not exactly words, but rather something called tokens. What tokens are basically the basic building block of AI language models. When you give text to a language model, it's going to first parse it down into these tokens, and then each token goes to the model, and then the model generates text using these tokens as well. So in general, these tokens more or less correlate directly to words, but there are some cases where these tokens won't. So for example, here, Llama's tokenizer will split the word cream into two separate tokens. But what's important to note is that although there's not a direct correlation from token to word, these tokenizers are public information. Doesn't matter if it's OpenAI's, if it's Meta's, you go through the entire list. you can get the tokenizer and you can learn the exact mappings. So for all intents and purposes, these are words, and we're trying to guess what these words are. So what's the threat model? So the victim types some private chat into his web browser, hits enter, and that encrypted text goes across the wire. Now, we're not going to be able to figure out what that prompt was, because that's just one big block of encrypted text. But what happens after that is the AI assistant starts responding token by token by token back, and we can count exactly how many characters are in each of these tokens. And once again, if we can guess what those words are, then boom, we know exactly what the response was. So why do we care? I mean, I can't figure out what the prompt was. I can't figure out what the exact question was. But it turns out that a lot of information is leaked by the response itself. So imagine I read one of the responses off the network that somebody was receiving, and it said, "I'm sorry to hear that you have a rash." Right? I think it's pretty clear we know exactly what that user was asking for. So basically this boils down to a big Wheel of Fortune game, right? Where I have to start guessing what those words are. And this can be a particularly challenging problem because, there's many different ways you can solve this puzzle. But it gets even more challenging when you think about real responses from these AI assistants, right? They're not just one sentence, they're typically whole paragraphs with hundreds of words. So how do we solve this problem? So we turn to the age-old solution, which is AI, and we look towards a task which is very popular, which is language translation, right? But here, instead of going from a language such as French to English, we're going to go from token length sequences to plain text English. And what we'll do is we'll train an AI with lots and lots of examples of these token lengths to real English, and we'll be able to translate them very effectively. In our case, we used a state-of-the-art model called a large language model, or LLM. And this is the exact same technology that's being used in AI assistants such as ChatGPT. I'm not going to go too much into detail how it works. Leave that for other YouTube videos. All right, so what's the entire attack end-to-end? How does it look like? So the attacker is looking through the network, looking for responses from a particular AI service, such as ChatGPT, sees the traffic going across the network, and records down the token length sequence from those packets. He then passes that token length sequence to his trained model, which has seen lots and lots of examples, and it predicts what it thinks the original plain text was. So there's something else we can do to make this even better. So if we just give our model random arbitrary text, it's going to do so-so. It's not going to do so great because, as I said, there's lots of ways we can solve that puzzle. But as it turns out, AI assistants have a very specific style of speaking, right? They're not just going to respond with some arbitrary sentence. They typically start with something like, "Oh, sure, yeah, I can give you a recipe for tomato soup," right? So there's a certain style that's intrinsically in those responses. So what I can do is let's say I'm trying to target Microsoft Copilot, I can send lots and lots of prompts to Microsoft Copilot and build a huge data set of responses. And those responses capture the style of that particular AI service. And once I have that, I can fine-tune my model on that, and I'll get much, much better results. And as it turns out, I can get something around 55% attack success rate. So more than half of the responses that we see in the encrypted traffic, we can decipher. Okay, so let's look at some examples. So on the screen here is the first sentences that we're trying to decipher. The first line is the original text that is being sent from the AI assistant, and the second line is our prediction. So sometimes you can see in the first example there, we get it right on the first go, and sometimes we make some mistakes. So for example, in the bottom there, the original response was, "Yes, there are several important legal considerations that couples should be aware of when considering a divorce." And then, if we look at the inferred response, we got, "Yes, there are several potential legal considerations that someone should be aware of when considering a divorce." So even though we had some mistakes in the words, it's very, very clear what was the topic and that the user was trying to ask the AI assistant. And then if we move over to entire paragraphs, we get something around a 35% attack success rate, which is also very significant, considering how hard it is to try and guess what all these words are. And since we're using AI models, this isn't a perfect science. We're using a lot of heuristics here, so we sometimes get it wrong. So here's some fails. So in the ground truth, it was something like, I would like to suggest some following strategies for team leaders to balance the needs of individual team members with the needs of the team as a whole. And we inferred it as, I would suggest the following strategies, so far so good, but then for film studios to balance the needs of production, so on and so forth, something that's completely unrelated. And sometimes it gets even worse, right? So here's a case where the response has something to do with apple cider, and we thought it had to do with coral bleaching. Okay, so it's not a perfect science, but what's interesting to note is that because we're using machine learning model, the model also gives us a confidence score. How confident it is that this prediction is correct, right? So what we can do is we can look, and we're trying to attack a particular token-linked sequence that we see in the network, we can try to look at the confidence of the model and say whether or not we should trust this inference or not. All right, so how common is this vulnerability? So, around the time of our disclosure, or prior to our disclosure around February 2024, nearly every major AI vendor out there had this vulnerability. And, when you start wondering, why is that the case? How do they overlook this seemingly obvious side channel? And there's a few reasons that might come to mind. First, perhaps they didn't think that token links are the same as word links, so maybe there was just a simple blunder. Or maybe they thought there's no way that an adversary can guess entire paragraphs of text. That's just too hard of a problem. But what I think is more likely the case is that it has something to do with the big AI gold rush, right? There's so many industries that are jumping on the AI chatbot idea and throwing it into services willy-nilly, and they're not really thinking about security by design. They're saying, the text is encrypted, not a big deal, let's move on, right? So this is probably more likely what happened there until they, of course, patched it after the fact. So why are they even sending, text streaming or token streaming across the network? Why don't they just send it as one big batch, right? So for example, Google's Gemini does this already. When you get a response from Google Gemini, it's not sending a token, it sends it as one big block, and therefore they're not vulnerable to the side channel attack. So why aren't the other vendors doing this? So there's a simple answer for that, and the answer is that these AI models are actually incredibly complex, and it takes a lot of effort to execute them. So instead of having the user wait there for a good 30 seconds for this loading screen to go by to get their response, it makes perfect sense to send those words or tokens one at a time in real time so they can read it as it's being generated. All right, so to recap so far, what we've accomplished here is that we've discovered a novel side channel attack, which we call the token length side channel. And we found it's common in LLM services all over. And we've also found a way to exploit that side channel, to read the hidden information behind it directly using AI, and improve that performance using a known plain text attack. Okay, so for the rest of this talk, we're going to get down into the nitty-gritty details. And first, we're going to talk about how we identified response traffic inside network traffic, and how we then extract the token length sequences from there. And after that, we'll talk a little bit about how we train AI models and our specific RAI model. And finally, we'll end off with some demos, defenses, and we'll talk about some bug bounties that we got along the way. So with that, I'm going to hand it off to Daniel, who's going to take it from here.
Thanks, Israel. So let's jump to the nitty-gritty details. So we will talk about how to find the side channel and how to extract the token length sequence. So the first thing we'll have to do is to capture the traffic containing the response from the AI assistant. So we'll need to be positioned between the victim and the AI assistant. Or we can be in the same local network as the victim, for example, sitting in the same cafe using Wi-Fi. So we collected a lot of traffic, and not all of it containing our response data from the AI assistant. So we'll need to filter the traffic. We can do that by filtering by the IP address of the AI assistant, That information can be collected by OSINT or by connecting as a legitimate client to the AI assistant server through different times a day from different locations and making our own data set of those IP addresses and basically filtering by those. Also, what we can do is filter by the protocol. So every vendor is using different protocol. For example, ChatGPT is using QUIC protocol. So we would like to search for UDP packets that are coming from port 443. And again, every vendor is using different protocol, so we'll need to account for that. And also there is a slight problem because it will add us more complexity when we will try to extract the token length sequence. Because again, every protocol looks differently on the wire and it has its own metadata. So we captured the traffic, we filtered out most of the traffic that don't contain our tokens. We have the traffic that contains the response from the AI assistant. Let's extract the token length sequence. So our objective is to find the token lengths. We need to remember that the traffic is encrypted, so we can't really see where are the tokens and what packets contain them. But what we can see is the bandwidth patterns, basically the packet sizes. Oh, I'm sorry. So we found that there is two main ways that the vendors are using to send their tokens. The first way is base plus next token. Basically, each token is sent in a separate packet by itself. So we can infer the size of the token by just analyzing the size of the packet. The second way is token accumulation. Basically, the tokens accumulate. We are sending each time the token with all of the tokens that were previously sent. So the packets are increasing in size. In the next slides, we'll talk more about token accumulation because this is the way that Microsoft and OpenAI are using. So basically, our main target was ChatGPT. So we'll talk about this more. So to simplify the problem, we'll first try to identify which messages, which packets are containing the response. So to simplify it, let's try to find the start and the end. So again, we can analyze the bandwidth patterns. And we found out that at the beginning, at the end of the response, we saw bumps, like increases in the packet sizes. That's because at the beginning you have all of those handshakes and establishing of the new channel, and at the end you have those communication of the end of the response. So you have those increases, and we can basically find the start and the end. Between those 2 points, the start and the end, we'll try to search for this incremental pattern, the red line that you see. The packets that follow this trend contain our tokens, but sometimes we have packets that don't follow this trend. Those are sometimes control packets that do not have our tokens, so we will filter those out, and we will be left after that filtering with a nice and smooth incremental pattern from which we can extract our token lengths by calculating the delta, as Israel said. So it sounds pretty simple, and some would say even easy, and too good to be true. And in reality, it's really the case, so we have more challenges. The first challenge is message size limits, and the second one is message buffering that will cause message groupings. So let's talk about that. Message size limits. In the internet, we have this thing called MTU, maximum transmission unit. Basically, a maximum size that the packet can have, and if we go above this value, we can be fragmented on the IP layer. And what we found is ChatGPT over QUIC has even a lower maximum size of 1,200 bytes. And as you remember, ChatGPT is accumulating its tokens. So at certain point, it will reach this maximum size. So what will happen is basically that the payload will overflow to the next packet. So now we have two packets that are sending this token because our payload is just too big. And what will happen is basically the sort of pattern that you see now. And also, as the conversation grows and goes deeper and deeper and makes it more and more long, we basically can also overflow to the third and fourth and fifth packet. And at the filtering phase, we'll need to account for that because we don't want to throw those packets. They contain our tokens. Another challenge is that the busyness of the network will cause basically bufferings that will cause our groupings. What does it mean? So when the network is busy and lots of clients are connecting to the AI assistant servers and many chat with ChatGPT, what happens is that the servers tend to buffer the responses. And what it looks for the user is that basically he has a small freezes that he sees. And for us, what it looks like is that some packets will contain more than one token, more than one new token. So basically this new packet will be double the size of the original trend. And what we can infer from that size is the sum of those tokens that are contained in a packet. But what we cannot infer is the size of each individual token. And this problem will be overcome in the next phase, which Roy will talk about, with exploitation with AI. So we will worry about that later. You probably wonder, how did we find all of this out? So we basically reverse engineered the traffic. We connected as a legitimate client to the AI assistant servers. We grabbed the SSL key, the encryption key between our computer and the AI assistant server. We plugged this into Wireshark, and we were able to watch the decrypted traffic, learn it, like analyze the metadata, and make rules to extract the token length sequence from the encrypted traffic. So to sum this up, we captured the traffic, we filtered the traffic, and then we extracted the token length sequence. And now we would like to translate those token length sequence to plain text English, and that's what Roy will talk about next in the next part, exploitation with AI.
Right. Thank you, Daniel. Let's indeed talk about how to exploit the side channel using a machine learning. But don't worry, I'm not a typical machine learning guy. We will keep it simple. So the first step in training a machine learning model is to basically gather a data set. We need to have a data set which will contain inputs and the outputs. Then we train the model by feeding him examples of the inputs and what the output should look like. Training an LLM is no different. So in our case, the attacker will first gather a huge corpus of text. He will transform the text into token length sequences and then pass them to the model. We hope that the outputs of the model, if not exact, will have the same similar semantic meaning. All right, so now begs the question, how do you even use the model? When LLM output gives you a response, an output, each time you get it a bit differently. As Israel said, each time with the output you get a confidence score. Then you can basically prompt the model many times and sort the outputs based on the confidence score. And most often, the most confident output will be the closest to the real thing. So that sounds really simple and fun, and that's what we did. We took the AI assistant response, transformed it into token length sequence, passed it to our trained model, and it failed miserably. Well, the problem was too hard, even for an LLM. But we still had a glimpse of hope, because although the semantic meaning similarity was nowhere to be found, the model still learned the high-level structures, such as list structure. So we started to look around on ways to improve our approach. We noticed a really interesting phenomena about AI assistant responses. The first sentence almost always holds the essence of the entire response. The first sentence is like an introduction to the coming paragraph. Learning from history, we took the hard problem and divided it into smaller problems to deal with each at a time. Because the first sentence is really unique, we first tackled it and tried to solve it, and then all of the others. Because if you think about it, if we crack down the first sentence, we would win. Because we could build upon that with a preserved topic in mind. But wait, hold on. Isn't the traffic encrypted? What do we even have in the end? Token length sequence. How are we able to divide it into segments of sentences? Well, most tokenizers encode punctuation marks as a separate token. This means that almost always a token length of 1 is a punctuation mark. So this means we can basically look at the token length sequence, search for a 1, and divide it. But we want to avoid false positives. For example, too short of a sentence because comma at the start. So we applied a simple heuristic that basically says we won't divide it if the sentence is too short. All right, with this idea, because the first sentence is really unique, we train the model only on first sentences, meaning its dataset contains only first sentences. And we train another model for all of the other sentences. To further help the second model try to figure out what is the right topic, we took the output, which was generated by the first sentence, and then passed it as part of the input to the next model. And then with other generations, we did the same. And just like that, we have preserved the context in mind when generating the entire paragraph one by one. All right, this approach is nice. And we got 10% attack success rate, but it's not enough. We are at DEF1 after all. So there is one more thing that could help us improve. As we said, AI assistant responses are not just random Wikipedia pages. They are not random text. This means they have predictable style and low response diversity. This means that we can use it to our advantage and relate to this problem as a known plain text attack. AI assistant responses have predictable style. They have warnings, templates, they follow safeguards and structure. This means that if we will train a model on those responses, the model will be able to learn those patterns, and it will make our life easier. Also, as we can see here, many different prompts that talk about the same rather topic will have the same response. This means that a model which is trained on AI assistant responses will be able to generalize to many different prompts. So, to summarize, the entire process is first collecting a data set of prompts. Then we will pass it to our target model, like ChatGPT-4. Then we will collect the responses, transform them into token length sequences, and train the model, as we saw. This combined approach yields a huge boost of performance. This plot compares the performance of the combined approach, the green one, the blue one, which is training the model on random text, and the red one, which is plainly asking ChatGPT, please help me solve this side channel. And we can see that all of the examples to the right of the vertical line are considered successes, and the green one was much better than all of the other approaches. And the numbers, as we said before, we got about 55% attack success rate on first sentences and 38% on entire paragraphs. We have also encountered a really interesting phenomena. Different topics were susceptible than others. In our example, mental health and financial status were much more susceptible than, for example, sexual health. This is mainly to the fact that those topics were much more common in the dataset. This means that if we have an attacker with a specific goal in mind, he can train his own model on those subtopics and get better results. All right, so what about the network noise and traffic and all of the stuff Daniel said? When we have high network traffic, we get grouping and buffering. So we first wanted to evaluate how much groupings were actually there. We ran a 24-hour experiment against OpenAI ChatGPT, and we measured the amount of groupings we got in each hour of the day. As expected, in the day, there were much more groupings than in the night. But as we will see, it is manageable. To solve this challenge, we took our training process and our dataset and just applied random groupings on the token length sequences. Then, as we can see in the first row, we still got 35% attack success rate on first sentences, which is really nice because it is way more challenging. Also, when looking around on different susceptible vendors, we found out that OpenAI API transmitted their messages as paired tokens, meaning each packet holded 2 tokens. Okay, this is more challenging, but we wanted to evaluate if we can break it and award more and get more reward. So we took our training process and applied and we applied pairing on the tokens, meaning we took the token lengths and just paired them. We still got 17% attack success rate on first sentences with this approach. All right, so after I've yacked you out with theory, let's talk business. So, as we all know, training an LLM from scratch is really hard. It takes months of compute time and millions of dollars in hardware and energy. We didn't have to go through such hassle. Rather, we used a common technique called fine-tuning, which means we took a trained model and further trained it on our own translation task. We took a model called T5, which was trained...
Pause for a second. We need to do a global announcement. Sorry. There'll be a small disruption, sorry.
Attention DEFCON hackers. Halls 2 to 4 are now closed. Heavy equipment will begin operation soon. All humans need to vacate the premises before they become trapped and are forced to become goons for eternity. Villages and contests have now closed. All hacking of the planet must be done elsewhere. Please join us for the contest closing ceremonies in track 1 and 2. Attention, DEFCON hackers. You must vacate the hall before you become impaled by a forklift. Thank you, and have a good day.
Okay, good day to you too. Yeah. So, let's recap. Our model was based on the T5 model, which is trained by Google, and it is publicly available. We also didn't have to go to the hassle of gathering our own dataset. Rather, we used an open source one called UltraChat, which basically contains dialogues with GPT-4. We also used Hugging Face as our framework trainer, which makes the technicalities of training a model much easier, even for a guy like me. Okay, our model was trained for 2 days of compute time. And if we have an attacker with no GPU in hand, he can use Azure, for example, for only $200, which is fairly affordable. So let's see some demos. In this case, we have the victim, query Microsoft Copilot. He asked the random question of what are some of the latest development in machine learning and AI that could revolutionize the health industry. Besides him, the attacker eavesdrops the entire traffic. He collects traffic using Wireshark. And after collecting for a bit of time, he will try to filter the traffic. As Daniel said, one of the common techniques to filter is based on the IP. So the attacker does just that. And in this case, the attacker manually figures out where the start is. Well, of course, the traffic is encrypted, so you just need to do it by hand and by eye. And after figuring out where the start is, the attacker will put inside the tool the token lengths, the packet sizes. Then the tool will calculate the deltas between the packet sizes, and we will have a token length sequence. Then basically, the tool will pass it to the model to try generate the ground truth. And as we will see in a bit, hold on. Yes, we got the token lengths, and now the model thinks actually really fast. And all right, so it will zoom out in a bit. We basically got the same rather topic. Several recent advancements in machine learning and artificial intelligence that could be a game-changing tool, yada yada. All right, so for the public use, we've deployed a full plug-and-play tool on GitHub called GPT Keylogger. The tool has 2 main modules, the attacker module and the trainer module. I will elaborate them in a bit. And our model is also publicly available, and it is trained on ChatGPT-4 responses from February 2024. The first module, the attack module, is for you guys to try attack different vendors. It can receive as input packet lengths, as we saw in the demo, token lengths, which is straightforward, and the original text. The tool will basically tokenize the text, calculate the token length sequence, and try to predict. And you can use it with this simple command. If you want to target a different vendor with a different backend LLM, you should train your own model. Because every LLM works differently, and our model is based on GPT-4 responses. So if you want to target a model like Llama, you should train. And we offer this for you to make life much more easier with those commands. Also, the configuration file is also available in the GitHub page, which is nice. And all right, so let's talk some defenses. We have contacted all of the vendors that we found vulnerable up to February 8th this year. All of the major vendors were really responsive, and they patched the problem really quickly until March 1st. And we came public with this vulnerability on Ars Technica on the 14th of March this year. Out of the vendors, those 5 had bug bounty programs, which awarded us a small reward, which was really nice. All right, so although this side channel is really difficult to exploit, as we saw, the defenses are really easy to make. After consulting with the engineers of the different vendors, we came up with 3 solutions. Random padding to the packets, padding to the nearest value, like nearest 100 size, or applying more buffering. Here is the mapping between the different vendors and the deployed defenses. When diving a bit deeper, OpenAI basically did padding to the to the closest 32 value by adding a pad field on the transmitted JSON. And as we can see on Wireshark, the sizes align. And Cloudflare, for example, deployed random padding. And we can see that the sizes are all messed up. All right, let's wrap things up. So, what did we discover? We have identified a new side channel vulnerability based on token lengths. This is significant because, as we saw, it impacts multiple vendors, exposing sensitive information through their AI systems. This work has shown how to break a side channel used with generative AI, and it is the first work to do so. While some vendors have patched this vulnerability, there is still a real concern about how new AI services will handle this issue. Now on to the key takeaways. First off, it is crucial to use encryption schemes correctly. This has repeated itself throughout history, time and after time, leading to multiple side channels and cracking of encryptions. Similarly, in modern times, even subtle details like token lengths can leak sensitive data if not properly protected. AI services are no exception to this rule. They must be designed and implemented up to the highest security measures as any other software domains. Remember, AI is your friend. It is a powerful tool both for offensive and defensive applications. We should harness its potential to identify and mitigate vulnerabilities. What seemed impossible is now possible, thanks to advancements in AI. Finally, our discovery raises an important question. What other side channels are vulnerable? We encourage the community to explore and secure these potential weak points. To sum it up, we have journeyed throughout the process of identifying, exploiting, and defending against this new side channel. This research highlights the importance of considering even the smallest details in data transmission within AI systems. I hope this inspires you to think creatively about both offensive and defensive capabilities of AI in cybersecurity. Thank you all for your attention. Check out our tool, GPT Keylogger, and our labs page when we update on more research. Stay secure, stay curious, and enjoy the rest short bit of DEF CON. Thank you.